All right, welcome back. So today we'll be still talking about electric field, specifically the electric field by charge distributions. Okay, the last time we talked about dipole. So dipole is two charges equal and opposite signs. So equal amount of charge but opposite signs. Okay, so separated by distance L. So then dipole P is a vector that is equal to the charge of each of the charge times Q or times L. That's a vector pointing from the negative Q to the positive Q. And many molecules, they are permanent dipoles because of the charge distribution within the molecule. So for H2O, so this part is -2, and the hydrogens are each +1. So then the dipole moment will be, as a result, will be dipole moment from one of the negative charges here with the hydrogen positive. So one dipole in that direction, the other dipole in this direction. So the total dipole will be addition of these two dipoles in this direction. Okay, so these molecules are called polar molecules. And for neutral molecules, they don't have like charge distribution within the molecular, but if you place them into the external electric field, then the electric field will make the molecules become polar. So these things are called induced dipoles inside the molecules. So because they have the net positive charge and negative charge in the molecules, then if you have molecules inside the electric field, so either it's an initially polar molar or induced polar molecules. So either way, they will experience a torque because there are two forces on the positive and negative charges pointing in the opposite directions. So the torque is equal to dipole cross E field. Okay, so in that sense, and then the potential energy within this system is P dot E. So tau being P cross E, and then U potential energy being minus P dot E. Okay. And then we had a focus on discussing the calculating electric field by charge distribution. So we start with the point charges, okay, and that's electric field by each of the source point here. You just sum all the electric field up by doing this in vector format, okay. So then for charge distribution for a particular shape of object, if either it's linear charge distribution, surface charge distribution, or in this case, a bulk distribution. So then you'll actually cut small pieces of that distribution and then calculating dq. So for bulk, you do rho dV. For surface, you do sigma dA. For linear, you do lambda dL or dx, okay, in that sense. And then integrates to the whole body, okay, to get the overall electric field at a particular point of interest P. So then calculating different scenarios, electric field equal to for point charge, this is the equation you use. Okay, for linear charge distribution, you are going to use this. You integrate through the whole line. Okay, so by looking at small dq, in that case, it will be lambda dl. And then in this case, surface distribution with sigma dA for the dq. And for the volume distribution will be rho dV for the dq. Okay, so and then the k constant is equal to 1/4 pi over epsilon. So you can either use 1/4 pi times epsilon, or you use the k value as constant. Okay. We look at the example for the linear distribution. So this is a random one, and then the conclusion. So we start with like just take a small piece out there, and then we integrate in the x direction and in y direction. So in x direction, you have this as your final answer. In y direction, the electric field is either this expression or that expression. Okay, depending on what parameters you are given as known. So you can check on the previous video on the derivation of these two results. So this is kind of X, Y, and Z probably coordinate system, but if you're looking in X, Y in direction on the X, Y plane here, in a polar coordinates where you have Z and R, okay, and then another like the phi angle and perpendicular to the z direction in that sense. Okay, so then the result you had previously, the x now being z and then the y being r. So by basically just changing notations there, then you get to these two expressions. So similar to what you had before. Okay, let's take a look on one example here. So we'll look at a couple more examples today. So this one, and then the other ones for the surface charge distribution. But let's take a look on this one, which is on the linear charge distribution. So it says a uniform line charge that has a linear charge density lambda equal to 3.5 nanocoulombs per meter. It's on the z-axis between z equal to 0 and z equal to 5. Find the electric field on the z-axis at these three locations, 6, 9, and 250 meters. How does this compare to the electric field produced by a point charge that is the same magnitude but sits at the middle of the rock? Okay, so let's take a look at them one by one. All right, so we'll sketch the problem first. In the z direction, that's the horizontal direction. And then you have this rod of charge sitting at between 0 and 5. So uniform charge, 0, 5. And then it's looking for E at 6 meters and 9 meters. Okay, and then somewhere far away there, 250 meters. Okay, so this is Z in the units of meters. All right, so we are going to use the Z component, so you can just flip one slice backward. So then this is the electric field in the along the Z directions, right? All at the Z, those locations for part A. So EZ is going to be equal to K lambda. We can just use the result 1 over R2 minus 1 over R1. Okay, because we are given those as distance, right? So distance to the left-hand side and then distance to the right-hand side of the rock. All right, so here being R1 here, okay, so this guy is R1 and this one is R2, okay? So looks like you can just plug in the numbers, right? So this is going to be K lambda, K is 8.99 10 to the 9th Newton's meter square over Coulomb square. And lambda, 3.5 times 10 to the minus 4 nano coulombs per meter times 1 over 1 meters minus 1 over. So if this is 6, right, our name will be 6 meters. So 6 meters. Okay, so for R2, it's 1 meter, 6 minus 5. R1 will be 6 minus 0, so 6. So that gives you 226, about 26.2 newtons per coulomb. Okay, so that's at Z equal to 6 meters. And then for B, so it's the same. You just plug in the numbers. Now, R1 being 9, R2 being 9 minus 5, which is 4. So easy in this case is K lambda, again, 8.99 times 10 to the 9th. You might just drop the units for right now. Just making sure they are in SI units. So 1 over 4 minus 1 over 9. Okay. So this will give you 4.37 newtons over coulombs. And C, the last one, easy, E at point Z, 8.99, 10 to the 9th, 3.5, 10 to the minus 9. Okay, so yeah, let's just ignore the units there. So 1.1 over 250 minus 1 over, in this case, would be, or actually, it's 250 minus 5 first. So 245 first and minus 250. Okay. So that gives you, see, 2.62 about 2.6 times 10 to the minus 3 newtons over coulombs. Okay, so that's at those three different locations. So it says, how does this compare to the electric field produced by a point that is the same magnitude and sits at the middle of the rod? So then we are assuming at the middle of the rod, there's this big Q, okay, which would be just the lambda times the length, the 5 meters times 5 meters, okay, that's the Q. So let's see. So Q equals to lambda times 5 meters, okay? So then E at that particular point, right? So equal to that guy should be equal to K, Q, and then R, separation from here to here. So that should be 250 minus 2.5, which is the middle of the rod, okay? So 8.99 times 10 to the 9, Q will be 3.5 the lambda times 10 to the minus 9, but times 5 meters, okay, over, and this has to be squared. 250 minus 2.5, and you squared it, okay? So you calculate this, and then you find this is about also 2.6 times 10 to the minus 3, okay? So these two are pretty much the same, all right? So that means, so you look at this, so when you're at 250, this is very far away from the rod, so, right? So when your distance is very far away from rod, then this is approximately just equal to, you have all the charge at the middle of the rod, okay? So which kind of makes sense, right? Because when you are far away, then this becomes smaller, okay? But if you are close to the rod and the distance are comparable to the length of rod, then you will calculate them like that, okay? Otherwise, you can just do the approximation of that K overall Q over the separation to the middle square, okay? All right. So let's go back to the slide. So then we have looked at the straight lines distribution. What about if you have a curvature lines like a ring? So in this case, if you have a ring here, like maybe a metal loop, right? So if that carries charge, so then what will be an electric field at the point nearby it, right? So for the easier one to start with, let's say if this is the center of the ring and then the z direction goes through that x, y are along the plane of the ring here. So what will be then at this location z, which is distance z, any number, could be 1 meter, 2 meter, 200 meter, whatever, away from the ring, okay? So for this one, so typically this is from the x to the x center. So you'll actually first just determine what will be the total electric field, what will be the direction of the total electric field, because that's symmetric. So chances are likely in one or two of the dimensions, you'll have electric field equal to 0. So you might just have the electric field in one direction or maybe two direction, okay? So if you think about that, take a small piece on the ring here of, say, now in this case, if you treat theta being the variable, so you are going from 0 and then go through the whole circle here, right? So d theta, because the line distribution here now becomes the arc length here, which is r times d theta in this case, and then times lambda. Okay, so r times d theta will be d of the s or x here, but times lambda, that gives you charge. The same here, across the center here, you'll find another r lambda d theta, right? Which will be giving you an electric field at this point in this direction, and then this guy will be in that direction. So the horizontal component by these two small electric field, they will actually cancel out because of symmetric. So then the resultant will be just in the z direction. Okay, so in this case, your E field is going to be just in the z direction. The same thing if you pick another point, this would be a symmetric part of the ring on the other side that will result in the cancellation of E field in the XY plane. So then only in the Z plane, okay? So with that, then let's take a look. On this one here, let me show you on the paper here. So a ring, and then goes Y, X, X, Y, and Z. Okay, so the small portion over here, lambda r d theta, okay, where this is angle theta, and that's d theta, the angle, small angle. So at point P, connect from here to there. So this is your derivative E in that direction, but its X component will cancel out its counterpart on the other side there. So then this is theta over here. This angle is phi angle. So then this is adjacent. The Z direction is adjacent to this hypotenuse. So derivative of ZE in Z direction should be derivative of E. And this is phi. So cosine of phi. Okay. All right. So then overall, electric field, that should be just in the Z direction, should be integration of dz, and then theta, right, from equal to 0 to 2 pi, okay? And that equals to integration, and dEz is that, okay? Where dE is going to be k dq over r squared, okay? So this is r. From here to here is the r over r squared. So k dq will be lambda r d theta. Okay, so this guy is your dq. That's your dq. Over r, r will be over r square, r to the square. R square will be this square plus this square, right? This is r. This is the. Oh, actually, I shouldn't say this as capital R, but small r. Let's do small r because this one is capital R. So small r there. So small r square, r to the square should be hypotenuse square, right? Equals to r squared plus z squared. Okay, so r squared plus z squared. And cosine of this phi. Cosine of this phi will be this, right, over this. So cosine of phi, which is z over square root of, so it should be over r, right? R will be square root of r squared plus z squared, okay, in that case. All right, so you are integrating d theta. Theta is your variable. This is a constant, not dependent on theta. This is constant, not dependent on theta. Okay, and then z is also not dependent on theta. So everything is constant. So it'll be just k lambda r times z over, if you want, this is square root of this whole thing to the square, and then this is square root, right? So you can say r squared plus z squared. Square root is 1/2, and then this is 1, so maybe 3/2. And then integration of d theta. So theta goes from 0 to 2 pi. So this whole thing then gives you 2 pi. Okay, so the result will be just 2 pi k lambda r z over r squared plus z squared 3/2 to the power of 3/2. Okay, so that's your total electric field, and then only in z direction. Okay, so your E is going to be just this guy, 2 pi k lambda r times z over r squared plus z squared to the 3/2 in the z direction. So that you can express in that fashion. Okay, so it might look initially a little bit complicated, but when you do the integration, it turns out everything is not dependent on the variable that you are integrating. Okay, so that would be your result. If you know z, say equal to 1 meter or 2 meters, right? You can plug in a number given r as whatever number again, could be 2 meters, 5 meters, and just calculating what will be the total electric field at point P over there. Okay. All right. So then going back to the slide. Now we can actually before that, before we go to the next slide, we can just take a look on if this z is very large. Okay, so if z is very large, right? Z is very large, then R becomes smaller compared to Z. So well, let's look at the paper again. So if Z is very large, R becomes smaller. So then this guy becomes smaller, okay, in the denominator. So this becomes smaller. So then Z to the 3/2 becomes Z to the 3rd, right? So then Z on the top here will cancel out Z. So for R greater than Z, your E then becomes just 2 pi K lambda R over Z square, because Z will cancel out the Q and then in the Z direction. So this then would be similar to, let's take a look on here. So also this guy will be because 2 pi R, that's the whole circumference, right? And times lambda, that's the total Q. So that's the total Q. So then that equals K Q over Z square times Z prime. So that's the E. So Z, if Z is very large, then distance, Z will be the R in that case. So this now approximate as the total Q at the center here and then Z distance away. So that's KQ over R square, okay? So you can approximate it as a point charge in that sense. All right. So the third example of the day here. So I think we have looked at the linear charge distribution in a straight line and a curved line, right? Simple ones. Now let's take a look on if you have a surface charge distribution, okay? So to start with, we start with an easy one here. So if this is a circular disk, okay, what will be then the E at this point? So similar to the previous example, you can pick a small, or in this case, you are actually take a small ring out of the disk, okay? So as R prime, this is a varying R prime, so it goes from 0 to the radius R here. So you integrate through from the small ring there and increment of dr prime for the ring thickness. And then from 0, R prime equal to 0 outward to the edge of the whole disk. Okay, so then you are integrated through the whole surface to get that E field. So we'll take a look at the one of the slides of one of the rings here for any arbitrary R prime. So then you are again, so for a ring, we had the result from the previous example, right? So we can just use it right away. Or you can derive it. It's not easy. It's not too difficult to derive, right? It wasn't too easy, too difficult. So use that, then just integrating from R prime equal to 0 outward to R prime equal to capital R. Okay, so that's the strategy. But let's take a look on how you actually do that. All right. So we are taking a piece of small, so this is a large disk. And then imagine there's a small ring somewhere. With this as dr prime, and this is R prime, okay? So for a ring, we know the E field from the previous example that is equal to, let me just copy it down, 2 pi K lambda R Z, and then over R square plus Z square, 3/2, and that's in the Z direction, okay? Now in this case, we are calling this having a radius of r prime. So instead of capital R, so that has to be changed into r prime. So that's changed into r prime. And then this one is also changed into r prime. Okay. And for what we have here, so in this case, instead of doing k lambda, okay, we will be doing actually sigma times dA. Oh, actually not, sorry about that. Sorry, we shouldn't use the previous one because this is not a line. Now this is like a small disk kind of type, so aerial distribution. Okay, so that's start again from here. So you're actually going to do this one. E is going to be so k 1 over 4 pi epsilon, and then you are integrating through the surface. Okay, and you'll do sigma dA for dq over r square, where r is, so this is where that your point of interest on here. This will be your r. Okay, so over r square. Okay, and but again, due to the symmetric, it should just have the E field in the z direction. Okay, so you are just you just need to focus on the z direction here. So let's say z. Okay, and this, if we call this angle to be theta now, this should be theta. Okay, so in the z direction over here, so you're going to have just cosine of theta. Okay, so cosine of theta, where cosine of theta is equal to the opposite over the hypotenuse. So this is the opposite. So you might need to use a little bit of your imagination. This is the hypotenuse. Now this is the right angle down here. So this is z over r, which is z over square root of r square or r prime square plus z square. Okay, so in that sense. So this guy now becomes k integration through the surface sigma will be the area charge density dA will be equal to this small kind of ring surface area. Okay, so that should be 2 pi r prime, 2 pi r prime times dr prime. Okay, and then over r square, which is actually square r prime square plus z square. Okay, so this is r prime square plus z square to be that. And then cosine of theta will be z square root of r prime square plus z square in that case. Okay. Now it looks like a little bit scary, but when you do the integration, but again, there's a few constants, you can put them in front of integration. So here, z is not dependent on r prime, 2 pi and theta, they are all constant. So you can do 2 pi first, k theta, and z, and integration of the whole surface. That means r prime goes from 0 to capital R all the way outward there. And in here, you'll have r prime on the top divided by, this is r prime square plus z square, and then again 3 to the halves, and dr prime. Okay. So the result of this one, it's actually integration of this guy So actually gives you 2 pi k sigma z, and then now integration is gone because you integrated. So r prime square plus z square, and then to the minus 1/2, because this is minus of 3/2, right? So raised by 1, okay? And you have, so maybe not straightforward to see this, but lower limit, upper limit. So let me do this. We can do the reverse way, right? We can do derivative of this guy. So derivative of that with respect to r prime square plus z square, right? Minus 1/2. So my derivative that will bring this guy the power minus 1/2 minus 1, right? And according to chain rule, because this now is r to the prime, so that gives you 2r prime, okay? So then this becomes, so this is like minus 3/2, right? Which is the result. And then there's a r prime there, so this guy is actually 2 times of r prime over r prime square plus z square to the 3/2, okay? And because you integrate it, so this is your final power. So then everything would need to be divided by 1/2, okay? So then divided by 1/2, that means multiplied by 2. Okay, so then it's that guy. All right. Oh, actually, this wasn't right. So you do derivative of that. So minus 1/2 comes down here. Okay. And then so you have a minus 1/2 there, minus 1/2 goes here, and then you have that. So this actually cancels. Okay. All right. So derivative of that actually equal to this here. So there's a minus here. When you do integration, it brings you a minus here into the result. Okay. So this is the result there. Then you plug in the r prime equal to r, and then minus that equal to 0. So then the result will become, so basically the 0 one comes first because the minus of minus will become positive. So 2 pi k sigma z, and then times. In the equation over here, so this will be minus of r squared plus z squared, okay? And then to the half to the 1 minus a minus of 1 over r prime goes to 0. So z there, and then 1/2. So that guy. So minus becomes positive, so positive. Okay, so then z to the 1/2, z squared to the 1/2 becomes 1 over z minus that guy. Okay, so your result is 2 pi k sigma z is 1 over z minus 1 over r squared plus z squared, and that is in the square root, or to the power of 1/2, that means square root, okay? And that should be in the z direction only, right? That's your final result for this guy, okay? All right. So now this is pi. So now it says show that for B, show that if Z is large, so then the electric field can be approximate equal to a point charge that has the same magnitude sits at the center of the disk. Okay, so we have E just in the Z direction equal to that guy. Let me just copy that down. 2 pi k sigma Z, 1 over Z minus 1 over square root of r squared plus Z squared. Okay, and that's in the Z direction. So if Z is larger, much larger than R, then this guy becomes just Z. Oh, actually, no, because this is going to be a small number here. So in this case, we actually do have to use the expansion of this term. Okay, so we need to expand this term and just keep the first order approximation. Okay, because we have this guy minus that one, so this guy will be smaller, little bit smaller than 1 over z. Okay, so then there's a small difference there. So we cannot just ignore the r square here because we are doing a subtraction here of two numbers close to each other. Otherwise, it's going to be 0, right? If you don't take the approximation, first order approximation. All right, so let's do, we can do z can go into the parenthesis, okay? So then this becomes 2 pi k sigma of 1 minus, so everything times z, right? So that means there's z on top, but you divide by then both numerator and denominator by z. So then on top it becomes still 1. But at the bottom here, you should have r square over z square plus 1. Okay, that's in the z direction. All right, so we need to expand this guy, basically, and just keep the first order. So this guy is it's 1 plus r square over z square to the minus 1/2 power. So basically, and then the expansion says this should be just the 1 minus 1/2 of this r square over z square, and then plus the higher order terms. Okay, so we can ignore the higher order terms, but if you want to write it out, this is like 3 over 8, and then r to the z to the fourth power, and then da 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 da. More higher order terms, but this one is already close to 0 because z is much larger than r, so this one is approaching 0. So this is the first order approximation. So take the inlet in this parenthesis here, you have 2 pi k sigma of 1 minus 1, right? And then minus becomes plus 1/2 r square over z square, and then plus da da da, smaller terms. So that goes to 0. And then this 1/2 and then 1/2 will actually cancel. So, and then again, this is only in the z direction. So your result should be just pi k sigma r square over z square. So pi r square will be the area for the whole disk, right? Pi r square, that's the whole disk. So a and then times this sigma, the area. So sigma times a. So then that is k q, right? Sigma times area, total area will be q over z square. Again, that's in the z direction only, z direction only. So this is again kq over r square, okay? So I think we have proved just that. If your r is much larger, then it's the same as you have a charge just at the center of the disk. And move on to part C. It says show that for a uniformly charged disk of infinity radius, the electric field is uniform throughout the region on either side of the disk. So now this time, R is infinity. R is much bigger. Okay. So again, Z, E in the only in the Z direction 2 pi K sigma Z 1 over Z minus 1 over square root of R squared plus Z squared, and just in the Z direction. So if your R is very big, R goes to infinity. So then this thing goes to infinity. 1 over that goes to infinity, right? So 1 over infinity then goes to 0, right? So then this is approximately equal to, so this is approximately equal to Z and Z will cancel, right? Just equal to 2 pi K sigma only, right? Z and Z cancel, and then in the Z direction. Okay, so this and doesn't depend on, so on the either side, right? It's going to be the same. So on that, on the flip side, it's going to be that doesn't depend on Z. So you can also, because of symmetry, so on the other side should be also the same. Okay, so it doesn't depend on Z in this case. So we have proved that as well. All right. So then if you plot it, for both sides of the disk, right? So then it's going to be just constant number 2 pi k sigma. And then, so on the other side should be pointing. So on the positive side, it goes up, right? On the negative side, it goes, the points down. So one side is positive, the other side is negative, okay? But both pointing away from there. E equal to 2 pi k sigma. Also, if you write this as k as 1 over 4 pi sigma, so you can see 2 pi, 4 pi cancels partially. So then it's just equal to sigma over 2 times of epsilon naught, okay? All right. So then later on, we'll talk about parallel plate capacitor. Basically, you have two pieces of plate that has charges on them. So then the electric field inside the between the two plates, right? Because by this plate, you'll have E equal to just sigma over 2 epsilon naught. And by this one, you will also have just sigma by over 2 epsilon naught. But if this is negative, then it's pointing in that direction. So those two field by the two plates will add up. So then 2 times of that. So then inside here will be just sigma over epsilon naught. Outside here, the E field by this plate is in that direction, by this plate is in other direction, so that cancels. So typically the outside will be 0, and then the same on the other side. E field by this guy will be in that direction, but by that guy will be in the opposite direction, so that also cancels out. Okay, so then it's 0. All right. I think we'll just stop here for today. Okay, so I will come back tomorrow for the next lecture. See you guys.